Welcome to our expert technical training on artificial intelligence workloads. Today, we are focusing deeply on identifying the specific features and capabilities of computer vision and image generation models. Welcome to our expert technical training on artificial intelligence workloads. Today, we are focusing deeply on identifying the specific features and capabilities of computer vision and image generation models. As enterprise architects and developers, understanding how machines interpret the physical world is absolutely critical. Computer vision is a foundational field of AI that actively enables machines to interpret, analyze, and understand visual information from the physical world. While humans use biological eyes, computers process digital images, videos, and live camera feeds. To a computer, an image is not a picture. It is simply a massive, multi-dimensional array of numeric pixel values. Each pixel typically contains a value between 0 and 255, representing specific shades of gray or color intensities. By algorithmically manipulating and analyzing these millions of pixel values, we create highly sophisticated software that effectively emulates human visual perception, enabling machines to fundamentally see the world. The enterprise scenarios for this workload are highly transformative. In retail, smart checkouts use cameras to automatically identify products like apples or bananas on a scale, instantly calculating prices. In security, computer vision powers robust facial recognition systems for facility authentication. In the automotive industry, autonomous vehicles absolutely rely on computer vision models to detect traffic lights, pedestrians, and road boundaries in real time, making split-second safety decisions. Throughout this session, we will explore exactly how these models work, from traditional neural networks to modern vision transformers, and how we can use them not just to analyze images, but to generate entirely new visual media from scratch. From an application perspective, capturing an image means loading these pixel arrays into memory. Your code will often convert an image file into a byte stream, or a base 64 encoded string, so that it can be securely transmitted over an HTTP network request to the vision model's endpoint. This flowchart visualizes the foundational computer vision workflow. Raw visual input is instantly converted into a numeric pixel array. The computer vision model then executes deep feature and pattern analysis, which directly powers critical enterprise scenarios, like autonomous navigation, smart retail checkouts, and facial authentication. When we talk about computer vision, we must identify the specific analytical tasks these models are trained to execute. The most fundamental task is image classification. In image classification, a model is trained using a massive dataset of images, each explicitly labeled with its main subject. When presented with a new, unlabeled image, the model mathematically predicts the most appropriate text label for the entire image. For instance, classifying an image as cat or dog. Moving a step further, we have object detection. While classification tells us what is in the image, object detection tells us exactly where it is. An object detection model is trained to identify the location of specific objects within a frame, typically outputting coordinates to draw a bounding box around each detected item. This is how a self-driving car distinguishes a stop sign from a pedestrian. The most granular analytical task is semantic segmentation. Semantic segmentation is an advanced form of object detection where, rather than drawing a simple box, the model actively identifies every single individual pixel in the image that belongs to a particular object. If you need to precisely isolate the exact outline of a tumor in a medical X-ray, semantic segmentation is the required workload. Furthermore, modern multimodal models combine visual features with associated text descriptions, allowing them to generate comprehensive natural language explanations of the detected items. To build these robust capabilities, the underlying machine learning models must be exhaustively trained on large volumes of existing images. As architects, you must match your specific business requirement, whether it is broad categorization or pixel-perfect mapping, to the appropriate computer vision task to guarantee optimal performance and accuracy in your application. When calling an object detection API, your code will receive a complex JSON payload in response. This payload does not just contain the predicted label, it includes an array of bounding box coordinates, typically represented as X and Y integers for the top left and bottom right corners, allowing your front-end UI to draw rectangles directly over the image. This diagram breaks down the three core analytical tasks. Depending on the question asked of the image input, the system branches. What is this? Triggers image classification. Where is this? Triggers object detection for bounding boxes. Exact outline? To understand how image classification and object detection actually function under the hood, we must explore convolutional neural networks, or CNNs. For decades, CNNs have been the absolute core of computer vision solutions. The defining characteristic of a CNN is its use of mathematical filters. The ability to use filters to apply effects to images is common in basic photo editing, but in computer vision, the goal is to extract deep meaning. A CNN applies hundreds of distinct filters across the raw pixel array of an image to systematically extract numeric features. In the initial layers of the network, these filters might detect very simple visual patterns, such as horizontal lines, vertical edges, or specific color gradients. As the data passes deeper into the subsequent layers of the neural network, The model combines these simple features to recognize much more complex shapes, like curves, textures, and eventually, highly specific object components, like wheels or eyes. This automated feature extraction is what enables the machine learning model to be trained effectively. By continuously passing large volumes of labeled training images through these convolutional filters, the network mathematically adjusts its internal weights to recognize the specific feature patterns associated with different object classes. While CNNs are incredibly powerful and have driven massive advancements in computer vision over the years, they require significant computational power to train. Understanding CNN architecture is crucial because it forms the historical foundation for how AI systems process spatial data, paving the way for the more advanced, multimodal transformer architectures we heavily utilize in enterprise cloud environments today. While cloud developers rarely write raw CNN convolution mathematics, understanding the underlying tensor transformations is key. If you were building a custom CNN using PyTorch or TensorFlow, your Python code would explicitly define convolute 2D layers, specifying the exact filter size and stride length used to scan across the image matrix during the training loop. Observe the convolutional neural network architecture. The raw image matrix passes through the first convolutional layer to extract simple edges and colors. It proceeds to deeper layers to extract complex shapes, which are then passed into the neural network processing core to yield a highly accurate object classification. While convolutional neural networks process images through filtering, the latest breakthrough in computer vision is the Vision Transformer, or VIT. Inspired by the massive success of transformers in natural language processing, researchers adapted the architecture for visual data. Instead of processing text tokens, a vision transformer extracts discrete patches of pixel values directly from the image and generates a linear vector for each patch. It then applies the exact same attention technique used in language models to determine the contextual relationships between these image patches. The transformer creates a multidimensional map of visual features like shape, contrast, and texture, based on how they co-occur. This breakthrough led directly to the creation of multimodal models. Multimodal models, such as the vision-enabled GPT-4.1 series available in Microsoft Foundry, can understand and work with more than one type of data simultaneously. They combine the visual embeddings generated by the vision transformer with text embeddings from the language model. This shared vector space allows the AI to discern deep semantic relationships between visual features and human language. Consequently, you can pass an image of a complex architectural diagram alongside a text prompt asking, "Explain the data flow in this architecture," and the multimodal model will analyze the visual layout, read any embedded text, and generate a highly accurate natural language response. This eliminates the need to build separate, brittle OCR and NLP pipelines, empowering developers to build highly intelligent, context-aware agents that can see and reason simultaneously. Interacting with a multimodal endpoint via the OpenAI Python SDK requires constructing a multi-part message array. Instead of passing a single text string, your payload includes a content list. This list contains an object with the text prompt, followed immediately by an image_URL object containing either a web link or the base 64 encoded string of your local image file. This visual demonstrates the multimodal processing flow. The image input is converted into visual embeddings via pixel patches and attention, while the text prompt generates text embeddings. Both map directly into a shared multimodal vector space, enabling the model to output a comprehensive natural language visual analysis. Just as multimodal models can interpret visual input and generate text, the exact same underlying architecture can reverse the process, taking a natural language text description and generating an entirely new, original image. This workload is known as image generation. By identifying the visual features statistically associated with specific language tokens, an image synthesis model can render breathtaking visual media from scratch. Within Microsoft Foundry, the primary models for this workload belong to the GPT-Image-1 family. For modern enterprise deployments, GPT-Image 1.5 is the most advanced choice, offering high-fidelity, photorealistic image creation, strict prompt alignment, and precise image editing capabilities. It supports text-to-image workflows, where a prompt like "a futuristic city at sunset" yields a complete image, as well as image-to-image workflows for creating variations. If you require a more cost-efficient option for high-volume, lower-latency tasks, the GPT-Image-1 mini model provides excellent performance trade-offs. Developers can immediately experiment with these models directly within the Foundry playground, iterating on their descriptive prompts until they achieve the desired visual style. Once the prompt engineering is perfected, the exact same generative capabilities can be accessed programmatically using the OpenAI Responses API. This empowers organizations to automate the creation of marketing materials, storyboards, and personalized application assets dynamically, unlocking unprecedented creative scale without requiring expensive graphic design software or dedicated human illustration teams. Programmatic image generation is executed using the images.generate method in the OpenAI Python SDK. You pass your descriptive text prompt and specify parameters like the desired resolution, e.g., 1024 by 1024, and the number of images to return. The API responds with a JSON payload containing a direct URL to the newly rendered Azure-hosted image. Here we see the image generation pipeline. A natural language prompt is sent to the Foundry Image Generation API. The system routes to the selected model, such as GPT Image 1.5 for high fidelity, or the mini variant for speed. The model synthesizes visual features to ultimately create the original image output. Expanding beyond static images, the frontier of visual AI now includes full video generation. In Microsoft Foundry, this incredible capability is powered by the highly advanced Sora models. Sora 1 is OpenAI's foundational text-to-video model, capable of generating short, high-quality video clips directly from text prompts, or by using a static image as a starting frame. It is heavily utilized for visual prototyping, storyboarding, and short animations. The next-generation model, Sora 2, currently in public preview, represents a massive architectural upgrade. Sora 2 supports not only text-to-video and image-to-video, but also video-to-video remixing, allowing developers to make targeted edits to existing footage without regenerating the entire sequence. Crucially, Sora 2 introduces synchronized audio generation and dramatically improved cinematic realism. Because synthesizing thousands of high-resolution video frames requires astronomical GPU compute power, video generation cannot happen instantly. From an architectural perspective, interacting with Sora models requires an asynchronous REST API workflow. When your application requests a video, it submits the prompt to start a render job and immediately receives a unique job ID in return. Your application must then systematically poll the API endpoint, checking the status of the job over several minutes. Only when the status returns as completed can your code securely download the final MP4 media file. This asynchronous design ensures the Azure cloud infrastructure can efficiently manage the massive processing load while keeping your client application highly responsive. Asynchronous workflows require robust state management in your code. Using standard Python HTTP requests, you first post your payload to the Sora endpoint to trigger the rendering process. Your code then enters a while loop, executing GET requests with an exponential backoff delay, e.g., waiting 10 seconds, then 20, until the JSON response indicates the video is ready for download. This diagram maps the asynchronous video generation workflow. The prompt is sent via a POST request to the Sora API, which immediately returns a job ID. The client application then repeatedly polls the GET request status. Once the status shifts from pending to completed, the system safely downloads the generated video file. As we conclude our deep dive into computer vision and image generation workloads, we must ground these capabilities in robust enterprise architecture and strict governance. Whether you are deploying a multimodal model for semantic image analysis or provisioning a Sora endpoint for automated video rendering, all of these workloads operate on a secure client-server architecture within Microsoft Foundry. Your client application is responsible for capturing the user's input, be it text, a webcam stream, or a base 64 encoded image, and transmitting it securely to the Azure-hosted model deployment. The server then runs the intensive inference tasks and returns the structured data or generated media. Crucially, deploying these powerful visual models mandates strict adherence to responsible AI principles. Image and video generation models must be actively governed by safety filters to prevent the creation of harmful, illegal, or deceptive content, such as deepfakes or copyrighted material. Foundry handles these security boundaries, quotas, and content safety filters natively. Thank you for joining this expert technical training module on identifying visual AI workloads. If you found this session valuable, please be sure to like this video, subscribe to our channel, and share it with your network. To truly accelerate your career and master these advanced cloud concepts, I highly invite you to visit quicktechie.com. We offer premium certification prep, featuring extensive Q&A banks, ebooks, audiobooks, advanced training labs, and expert interview guides. Build intelligently, innovate visually, and always deploy responsibly. Securing your visual AI architecture means permanently removing hard-coded credentials. Your production application must leverage Azure-managed identities to authenticate with Microsoft Entra ID dynamically. This ensures your client code can request temporary access tokens to invoke the Foundry model endpoints without ever storing highly sensitive API keys in your repository. Our final flowchart highlights the security and governance architecture. The enterprise client application authenticates via Microsoft Entra ID to hit the Foundry model endpoint. Every request passes through responsible AI safety filters. If the content is deemed safe, the system executes the workload and returns secure verified data.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.